Okay, thank you. I'm Katsuma Miyamoto from NTT DOCOMO. I'm in charge of reading the architecture of 5G core network at NTT DOCOMO. So today we would like to introduce our proof of concept where we implemented 5G core UPF function on DPU card and connected to our commercial network. And we also integrated with AI solution. It will be introduced by Paul. So, okay, let me briefly explain about 5G core network. Yes, so NTT DOCOMO is one of mobile operators in Japan. We launched 5G services in 2019, starting with 5G NSA. And so then we also launched 5G SA in 2021. So as of today, over 30 million users enjoy 5G services with 97% population coverage access across Japan. So 5G core network is positioned between radio area network and the internet. So it not only handles the user traffic, but also realize a function like session management and authentication. So in 5G core network, as you can see, there are multiple network functions like this. And so today we would we focus on the UPF. UPF stands for user frame functions that is handle user traffic. So in order to handle the user traffic, the GTP tunnel is used in mobile network. So for downlink, which comes from the internet to user equipment, UPF receives the IP packet from the internet. It's encapsulation with GTP and send them to the G-Node B. On the other hand, UPF receives a GTP packet from the G-Node B. It decapsulation them send them to the internet. So in order to handle the GTP tunnel, UPF have to communicate with SMF to receive the session information. And UPF also has various functions like this, such as QoS, packet counting, packet reporting. Yeah, that is unique to the mobile network. So because of this, so we have been exploring UPF implementation on DPUs. So the detail will be explained by Siku in the next part. But the ARM CPU on DPU handles the PFCP processing and slow path as well. And the network processor on the DPU is responsible the fast path between G-Node B and the internet. So by implementing the 5G UPF functions on the single DPU, it could be ideal for the edge use cases. So we call it this UPF. We call this UPF distributed UPF or DUPF. So so Shiku will explain the detail of the implementation.
Hi, I'm Shikuhirai from NTT DOCOMO. So I was a member of NTT R&D until September, and now transferred to the DOCOMO's core network design department. And so I'm in charge of design and development of DOCOMO's commercial 5G core networks, same as Miyamoto-san. So I will talk about the distributed UPF. We call it the UPF on DPU. And this is the detail of our DUPF architecture on Bluefield 3 DPU developed by NTT R&D. So UPF slow pass is a container running on Bluefield 3 ARM cores. And UPF slow pass is responsible for the data plane session control, cooperating with the control plane functions of 5GC. Through the N4 interface defined by 3GPP standard. And UPF Thropas uses PSCP as a communication protocol via control plane functions of 5GC. For the control of data plane session, we called UPF FastPass. We are using mainly Docker Flow API. And main tasks required for UPF, such as GTP encap, decap, and QoS processing, are processed at the connected 7E switch integrated into Bluefield 3. And our new UPF can be combined with some value-added functions needed in the telecom networks, such as IPsec. Both UPF slow pass and more intelligent processing can be launched not only on the ARM cores within the DPU, but also on the host side CPU cores. We aim to enable the selection of the optimal configuration based on demand and requirements. For example, in use cases requiring large-scale requirements or more advanced computational processing, we believe it is appropriate to launch on the host side CPU cores. On the other hand, when small scale or limited functionality is sufficient to launch on the ARM cores on the DPU side, and that full DP offload architecture is appropriate. And NTT R&D have started the collaboration with NTT DOCOMO since last year to challenge interconnecting the UPF and DOCOMO's commercial 5G and LAN. We contributed and exhibited our DUPF at Interop Tokyo in June this year. Interop Tokyo is the largest internet industry showcase in Japan. And at this event, we performed the experiments to connect DUPF to the DOCOMO's commercial 5G and RAN, and verified several scenarios. As shown in this diagram, we only devices with dedicated SIM cards were actually accommodated in the DUPF. And LAN and 5GC functions other than DUPF were running on the commercial environments, actually accommodated the other general user devices. And the video streaming and LLM services previously hosted on Interop Tokyo have been provided to devices with dedicated SIM cards through the DUPF and DOCOMO's commercial 5G networks. And this shows the system rack overview at Interop Tokyo. And our DUPF server hosting Bluefield 3 cards is here. And so at this time, so we supported two key features for interoperability with commercial networks. The first is that UPF must follow notifications of user session state changes from SMF. SMF is one of the 5G core network functions and responsible for the management of user session statements. And so we supported the dynamic control of flow rules on DPU to follow changes in user session statements. So this enabled various procedures such as handover and incoming call with packet buffering. So we tested the handover procedure while connected to the actual commercial networks at Internet Tokyo. And the second is filtering things. So we supported the filtering specific user packets on DPU. This enables SDF filters for local breakout to the MAC and charging operations. The SDF filter is rules defined in the 3GPP standard for granular traffic control on a per user basis. And we tested that specific packets could be locally broken out to the MAC, while other traffic could be routed to the internet side. And also, we integrated our DUPF with F5 products and services to validate future AI native network architectures alongside several use cases. These slides and videos shows some example. For example, model routing based on language identifications and assistance of LLM response by using system prompts, and also application of security policies against prompt injections. However, so there are still remaining issues for commercial applications. For example, we need more complex user level flow configurations. For example, we need the QoS and charging rules per user basis. And of course, monitoring, observability, and redundancy are the essential for telecom network. So we need we need those supports in the future. And finally, so let me to express our expectations for OPI from the operator's perspectives. So the first is we require vendor agnostic APIs to control multi-vendor DPs. So at this time, we used previously, but we are open and also interested in other vendors' DPUs. So we hope that dependencies on each vendor's SDK will not be required and cared. And the second is long-term support for DPU-based platform and solutions. So we also expected the creating ecosystems and for long-term support for DPU-based platform and solutions. I would appreciate it if we could continue to discuss on these and other matters in OPI communities. Thank you. I will switch for some.
Thank you very much. So I'm going to start by saying, so my GitHub handle is PDB2shirts, and I'm going to be wearing two different shirts here today. One is an F5 shirt, and one is an OPI shirt. So start from an OPI shirt. How is this relevant to OPI, and what does it mean for OPI? This POC and this solution, it's actually out in the market. This solution in the market is relevant to OPI because Balazs in one of his, early in his presentation, talked about big IP being one of the next workloads that we wanted to run on a DPU. So this is I'll show you here in a minute, this is a solution that runs the big IP traffic management microkernel, the core of our big IP platform, on a DPU. So we're getting to that next level there. This solution is, from an OPI standpoint, about where we were 2 years ago when we were building Nginx solutions and running them on DPUs. Quite a manual process. Wasn't the place where we could take and deploy that workload across multiple DPUs easily at this point. So that, just to set the stage, that's where this solution is as far as OPI. It's in we've proved that it will run on a DPU, one type of DPU. Now it's up to F5 and OPI to work on how do we get that to work across the industry of DPUs that are out there, DPUs and IPUs. So that's my OPI hat. That's where this presentation fits with OPI. Now to put on my F5 shirt and talk a little bit about what we've done here and how we've done it. So so the names are changing here, and I'm not the marketing guy, but is Big IP next for Kubernetes on a Bluefield 3, or you've also saw it's changing to Big IP next cloud native functions on a Bluefield 3 DP. I mean, it's a product name from, I don't know who made it up, but it's a long product name. Anyway, what does it do? It runs our Big IP core system on, we've ported it to ARM, so it will run on an ARM architecture, and we're currently validated running on a Bluefield 3. What does it do? Some of the things that this does tackles a multi-tenancy problem, and I saw in some of the other sessions that that's an issue, especially in the automotive session. I thought that was an interesting tie-in, where in the automotive session, the tenants were a safety secured area of the functions that needed to happen, and then a more infotainment session. So our solution here is an ingress and egress solution into a Kubernetes environment. It gives us the ability to tie Kubernetes namespaces back to data center networking constructs, be it VLANs, VXLANs, BGP, those sorts of things. So on whatever you're using to move traffic and secure traffic and segment traffic within the data center, this solution keeps track of namespace to that outside data center networking object. So now Coke and Pepsi can co-reside on the same cluster. They can use the same AI cluster. We can segment and multi-tenant that cluster and use the Big IP to keep that traffic separate. Namespaces keep it separate within Kubernetes. Our product keeps it separate in the data center networking space. So together, it's a full multi-tenancy solution. Yes, we've got rich observability, and we can do some fine-grained traffic management. One of the things you also saw was that very similar to what we did with the early Nginx demo, where we had Nginx running on the DPU, and we had an AI workload running on the host. We're doing the same thing in this demonstration. We're running the Big IP traffic management microkernel on the DPU itself, and then sending that traffic securely to an AI. In this case, it was an AI gateway or an AI guardrail solution that did prompt injection security and that sort of thing running on the host itself. So that's what we did there. I'm getting the shepherd's hook. So I think I've got one more slide, but I will just cruise to it. The other thing to note here is that throughout this session, we've seen several other workloads that are running on DPUs. So the distributed UPF is a workload that runs on a DPU. In this instance, we're running 2 DPUs in a host. One's running the distributed UPF functions, and one is running the Big IP functions. We've seen Nginx running as a workload. We saw the automotive stuff running as a workload. We saw Dash running as a workload. So I'm heartened that it's not that we're seeing, from an OPI perspective, we're seeing multiple workloads now running on these cards and being seen as valuable to customers, such that they're spending money to buy these workloads that run on these cards. So again, did you guys have any extra slides, or was this it? This the last slide? Okay, this is the last slide. So I think with that, I can stop and ask if there are any questions, and if not, we'll go from there. And I think it's maybe lunch? No, something? Oh, one more session. One more session. So, any questions?
Just one question on the has this been tracked any source code implementation, or it's the UPF is any like any open source code implementation, or it's
basically our in-house solutions our in-house code.
Yeah.
Can we bring this to one of our blueprints in OPI?
Yeah, I think that's the next step is taking this solution and seeing how we put it in OPI and how we make it work across multiple vendors' cards. And I'd really love to see how do we make it easily deployable as well across those cards.
In your setup with 2 DPUs, which is also something we're looking at, it's maybe like a prerequisite for this, I would say.
It is right now just for the power required,
Okay.
the processing power on the cards. So maybe if we had a different card in the lab that had more power to it, we could do it on one.
And then a more detailed question here is then the UPF is on one, and then does it talk through like hairpins out, or how do you cross from DPU to DPU, or do you go through the host?
It's house, yeah. So he just said it was outside. So it's a network
Hairpinning,
connection
okay.
from one to the
Okay.
other.
Okay, thanks a lot. Thanks, Paul.
Thank you.
Thanks, Shikuhira-san and Katsuma Miyoto.